Piecewise functions are functions that are represented by a combination of equations, each corresponding to a part of the domain.
Piecewise functions can take a variety of forms. These can include constant, linear, quadratic, exponential, and many more. If the piecewise function is continuous, it means that there is no breaks in the graph at all. If it is discontinuous, then there are breaks, and that is generally seen as a step function.
Alright, so the first thing you guys need to do is find out what the function is. So you're going to evaluate it, but the first thing you need to do is find what happens at the change. So you take your function, and you can see that the change occurs at 0 in this particular one. It's not always going to be at 0, but just for the matter of simplicity, I like it to be at 0. So, to evaluate that, we're just going to plug in 0, or wherever the change is, for x in our equation. So we're going to have f of 0 is equal to, and we're only going to put it into this top part for now, because I like doing this in 2 parts. So, 0 minus 2. So, that's basically it, and you just keep going. 0 minus 2 is just negative 2. So that's going to give us our first point to graph. 0 is going to be our x coordinate, and negative 2 is going to be our y coordinate. Because it's not equal to, and because 0, the number that we used before to evaluate it, is not included in the graph, we're going to use an open-ended bubble. So just, alright. Continue to solve it. We're going to think of a number that conforms to this definition. Because basically all this is saying is f of x is equal to x minus 2 when x is less than 0. So we're going to find any number you can imagine that's less than 0. So I'm going to be really creative. I'm going to use negative 1. So f of negative 1 is equal to negative 1 minus 2. Alright? So f of negative 1 equal to negative 1 minus 2, that's just negative 3. So again, x value, y value, graph that up. So negative 1, we go to the left 1 and down 3. And because we found one that does conform to that, it's going to be a solid bubble. And the downside to me picking negative 1 is they're really, really close. So my line's probably terribly inaccurate, but you just draw a line right through it. There's nothing complicating it. It is just a linear equation. So that's why I used a line rather than a parabola on part 2, which is just doing the same thing with this other one right here. So if you look over here, you can see, because it's x squared, it's going to create a parabola rather than a line. Summer job that pays time and a half for overtime. That is, if you work more than 40 hours per week. Your hourly wage is for the extra hours is 1.5 times your normal hourly wage of $7. Alright, so that's our story. We need to write and graph a piecewise function that gives us our weekly pay in terms of P, the number of H, terms of the hours that we work, rather, sorry. And find out how much we will get paid if we work for 45 hours. To look something a bit like this. So pay in terms of hours is equal to 7H. Get that because it's 7 an hour. When if 0 is less than or equal to number of hours worked, and the number of hours worked is less than 40. There we go. Sorry, I have to keep checking my notes. All right. Then we've got 10 hours, because this is 7 times 1.5 minus 140. Whenever H, that looks like a B, my bad, is greater than 40. So we're going to start with part 1 here, and just because of the way the word problem is structured and kind of just how numbers work, I'm going to use 40 as our point of change. So I'm going to use 40 for H. So let's see here. P of 40, oof, that was terrible. You can still read it. Is equal to 7 times 40. And so P 40 equal to 280. Alright. So then now I've got 40 hours and 280. Let's look at that plane over here. 40 goes up, 200, 250, kind of somewhere right about in here. And with that one, it is equal to, so we're gonna do a nice little bubble. All right. And then, so with this particular one, it's whenever H is less than 40, but greater than 0. So I'm just gonna use 1 to kind of keep it simple. Now, let's move on to part 2. We're going to do it with the change at 40. Anyways, what we did was P of 45, because it's a much larger number than 41, that ends up giving me more of a change that I can graph off of. Makes it more accurate for me. 10.5 times 45 minus 140, so 10.5 times 45 gives you 472.5 minus 140, and that's how we got to 332.5. Alright, so this is going to be our next point. We're graphing at 45, 332.5, jack up, just like that. So if we would have continued, it would have kept going like this way, but because of that break, it jumps up. Right? And that's a business application.
So if you want to apply step functions in everyday life, you can then start with this example of parking garage rates on the weekends. So for every half an hour you pay $3, and every half an hour after that you'll pay an additional $3 up until $8. The maximum that you can pay is $8, and that will cover 12 hours. So if you want to write a function for this, you allow yourself to call the amount of time that you're parked t. And it's really very simple. So you just write out a basic function, f of t. So if you want to plot these points, you're going to come over to this graph. So you'll take the 3, your line will be set at 3 and a half point. So here's our half point mark right here. Because the first mark here is not equal to, you use an open point. So right here, and then not a very long line at all, that long, and then the next mark is equal to, so you're going to use it for the dot right there, very, very small line. The next one you will mark at 6, so moving up here to 6, and it'll just be a little further out, so moving at half, you're going to use an open circle to 1, and a filled in circle because it is equal to. Then moving on up to 8, you'll start at 8 and you'll have your open circle at 1, and then you move all the way over to 12, so it'll be a long line there, and that is your completed